Okay, welcome everyone. Today we're doing a deep dive into a really interesting area where material science meets safety. We're talking about intumescent thermoplastics and polymers.
That's right. Materials that don't just sit there when things get hot.
Exactly. I mean,
Right.
think about the intense focus on fire safety everywhere right now. Huge buildings, massive energy storage systems popping up, safer electric cars.
The demands are increasing dramatically.
And engineers, well, they need stuff that goes way beyond just slapping a fire-resistant label on something. They need materials that can actually handle, like, extreme temperatures, really fast thermal events, things like thermal runaway, which is a huge concern.
Absolutely.
So our mission today, based on the source material we've gathered, is to really demystify these intumescent materials. What are they? How does that almost magic swelling work? And, why are they being talked about as potentially outperforming stuff we've used for ages, like mica and aerogel?
It's a fascinating area. And you mentioned the stakes. They really couldn't be higher, especially with the boom in high-density energy storage. Lithium-ion batteries are everywhere.
Right.
So the core goal, as the sources highlight, is creating effective passive fire protection. Basically, safety measures built right into the system design. Things that can isolate a dangerous thermal event, contain it where it starts, and stop it from spreading and causing catastrophic failure.
Built-in safety, not just an afterthought.
Exactly. And yeah, engineers have used things like coated metals, special plastic enclosures, layered composites, but the sources point out that regulations are getting tougher. And people are looking for solutions that are, well, more robust, don't pick up as much space, and frankly, offer better value overall.
Which leads us right back to these intumescents. Okay, let's unpack this. What are they, fundamentally?
Well, at their core, they're engineered plastics. But they have this incredible characteristic.
A superpower, almost.
You could say that. When they get exposed to high temperatures or even direct flame, they expand dramatically.
And the numbers are wild, right? The sources mention some can swell up, what, 20 to 80 times their original size?
Yeah, that's the kind of range we're talking about. It's significant.
Mm.
And as they expand, they form this tough, insulating layer called a char.
Ah, the char layer. That's the shield.
Precisely. That's the protective barrier. And the sources detail several key properties that make them so effective. First, obviously, is that thermal expansion. That massive swelling creates the physical barrier, the char, separating the heat source from everything else around it.
Okay, makes sense.
Then there's heat absorption. Now, this is where it gets really interesting, I think. The intumescent process itself, the swelling, is often endothermic.
Endothermic, meaning it takes in heat.
Exactly. It absorbs thermal energy from its surroundings. So it's not just blocking heat, it's actively sucking heat out of the immediate area, helping to lower the temperature and slow down that thermal escalation. It's an active response.
Wow, okay,
Yeah.
so it's not just a passive wall.
Not at all. Then you've got structural stability. A lot of plastics, even flame-retardant ones, might melt or deform pretty quickly at high temperatures. These are engineered to hold their shapes, maintain integrity for longer during a fire event. That's crucial for containment.
Right, you need the barrier to stay put.
And a really big one highlighted is design flexibility. Because they're thermoplastics, you can injection mold them or extrude them into really complex, precise shapes.
Like specific parts for specific jobs.
Exactly. Think intricate bus bar caps in an EV battery, or custom cell holders, or specific fittings for electrical fire stops. You can build the fire safety right into the component's design instead of just, wrapping something around it later.
That sounds much more integrated.
It is. And finally, it adds up to enhanced fire resistance. You might have a standard plastic that passes, say, a UL 94 V0 test. That's good. But the sources argue these intumescent materials show resilience in much tougher, real-world situations, like actually containing a thermal runaway inside a battery module. All these things together make them really well-suited for advanced passive fire containment.
Okay, so how does this incredible swelling actually happen? Let's get into the science a bit. Based on what the sources describe, it sounds like a chain reaction.
It is, yeah. It's an engineered sequence. So when the material gets hot enough,
The trigger temperature?
right, that heat starts the thermal decomposition of specific additives mixed into the plastic. These additives break down and release gases, often things like water vapor, carbon dioxide, nitrogen.
Okay, so gases are released.
And those gases are the driving force. They cause the rapid volumetric expansion. They basically inflate the polymer matrix, puffing it up into that foam-like structure.
Like baking bread, but much faster and hotter.
Huh, sort of, yeah. And this creates the insulating char formation. That char is typically very stable and a poor conductor of heat. Plus, as it swells and fills the surrounding space, it also helps with oxygen deprivation.
Cutting off the fuel for the fire.
Exactly. It limits the oxygen that can get to the heat source.
And you mentioned this can be engineered, like you can set the temperature it kicks off at.
Yeah, that's the clever part.
Yeah.
By choosing different additives and formulations, manufacturers can tune that trigger temperature for specific needs. And the sources also make a point of saying these materials are tested to make sure this firefighting capability doesn't mess up their normal mechanical properties needed for everyday use.
Right. It still has to work as a regular plastic part until things go wrong. Let's go back to that design flexibility because molding complex 3D shapes sounds like a huge advantage compared to the older ways.
It really is. Think about traditional materials like mica sheets or aerogel blankets. The sources point out you often have to take these flat materials, maybe cast them first, then cut them very precisely, stack them up in layers, maybe use special tapes or adhesives to hold them together and seal the gaps.
Sounds fiddly. Lots of steps, lots of chances for error or gaps.
Exactly. Much more labor-intensive and potentially less reliable if not done perfectly.
So the sources give an example of this.
They do, a really compelling one. High-voltage busbar caps in EV battery packs. Picture this. You've got these copper bus bars carrying hundreds of volts running just millimeters away from other live terminals inside a packed battery.
Okay, tight space, high power, what's the risk?
An arcsing fault, like a short circuit, but incredibly intense.
Yeah.
We're talking temperatures potentially hitting 1500 degrees Celsius in microseconds.
Wow. Milliseconds.
Yeah, and the scary part is many standard engineering plastics, when hit with that kind of heat, can break down and release conductive gases, carbon, essentially.
Oh, so the plastic itself could help the arc jump further.
Precisely. One source had this vivid description like lightning inside a volcanic eruption within the battery pack itself. Extremely dangerous.
Okay, so how does the intumescent cap help there?
So imagine an injection molded cap made from an intumescent thermoplastic that wraps around the bus bar connection. According to the material, it offers several layers of defense. First, it has high dielectric strength. It resists electrical current flow, helping prevent the arc in the first place.
Good start.
Then, the material might include specific minerals that, when heated, release water vapor. This helps dilute any flammable gases that do form, reducing the risk of ignition and also cutting down on potential air pollution from the event.
Interesting. Releasing water.
Yeah. The surface material might also undergo a phase change, absorbing heat to shield components. And then the intumescent reaction kicks in, maybe around 200 degrees Celsius in this specific example.
Okay, here comes the swelling.
Right? It starts absorbing heat. That endothermic effect we talked about, it provides fire resistance, and it expands physically, maybe say 2 or 3 times its volume in this specific application. This expansion creates that insulating char layer, helping to physically isolate the arcing event and contain any resulting thermal runaway locally.
That's a fantastic example. It really shows the multifunctionality. So moving beyond that specific case, what other broad applications are mentioned? Energy storage systems seem like a big one.
Huge, especially with lithium-ion batteries. The big fear there is thermal runaway propagation. You have arrays of cells packed tightly together.
Domino effect. One goes, they all go.
Potentially, yes. So the sources describe using Intumescent tech right at the individual cell level. They mentioned a product example, LithiumPrevent, I think it was called.
Okay.
The idea is this material activates rapidly around a single failing cell. It expands, helps starve it of oxygen, and creates a barrier to try and stop that initial failure from spreading to its neighbors. Early containment.
Makes sense. But what about the whole module? Sometimes one cell going releases a lot of energy, right?
It does. Heat, pressure, gases. It can be intense and compromise the whole battery module structure. So there's also a need for module-level containment. Intumescent materials designed for this level are engineered to handle that larger energy release. They absorb more heat, reduce thermal bridging, that's heat conducting easily between cells, suppress potential electrical arcing within the module, and help isolate the entire unit if needed. It's like a crucial second line of defense.
Okay, so cell level and module level protection. What about cars, EVs?
Similar challenges, really. You've got those high voltage bus bar arcing risks we discussed, and the cell-to-cell thermal runaway concern within the main battery pack.
And car makers are always focused on weight and cost.
Exactly. They need materials that are super robust for safety, but also lightweight for efficiency and range. The sources point out that traditional approaches layering lots of insulation blankets or using heavy, bulky metal covers can add significant weight and manufacturing costs.
So intumescents offer another way.
That's the potential highlighted.
Mm.
Think about components like those bus bar covers again, or the spacers between cells, maybe even parts of the battery pack lid itself. If these can be injection molded from intumescent materials,
Then one part does multiple jobs.
right, a single component could potentially provide the electrical insulation, the arc protection, the heat absorption during a failure, and contribute to overall structural integrity and occupant safety by containing an event within the pack. By forming that protective char when needed, they're presented as being able to stop thermal runaway at the source, which buys absolutely critical time.
Buys time for people to get out, for first responders. Crucial. Okay, so we've heard a lot about how impressive these materials sound, but how do they really compare, according to the sources, against the older standbys like Mica and Aerogel? People have used those for years.
They have, and they serve a purpose. But the material we reviewed draws some clear distinctions, especially for these newer, high-energy applications.
Okay, what are the limitations pointed out for Mica and Aerogel?
Well, first, there's weight and bulk. Mica is noted as being relatively heavy and rigid. Aerogel is light, but can be bulky in blanket form. Then, integration complexity.
We touched on that, the cutting, taping.
Right. The sources say both often need extra sealing or adhesives, adding steps and complexity. Aerogel blankets are mentioned as being brittle, needing careful handling and complex layering. Cost and handling is another factor. Aerogel can be expensive, and dealing with the dust and brittleness can be tricky. Mica can be labor-intensive to cut and shape precisely.
Okay, practical issues. What about how they actually work in a fire?
This is maybe the biggest difference highlighted: passive burial versus active reaction. Mica and aerogel are fundamentally passive insulators. They slow heat down. But once the heat gets too high, they don't. Well, they don't do anything else actively.
They don't swell up or absorb heat endothermically.
Exactly. They don't have that intumescent reaction. Which brings us back to design flexibility, molding complex intumescent parts versus the difficulties of shaping mica without it flaking, or dealing with brittle, powdery aerogel that usually needs to be encapsulated.
And finally, flame retardancy itself.
The sources present it this way. Mica and aerogel insulate well, but they aren't really designed to actively suppress flames or stop ignition and propagation by cutting off oxygen and forming a robust char like intumescents are engineered to do.
Okay, so summing up that comparison.
Essentially, the sources argue that intumescents offer the insulation plus that dynamic active response. The endothermic cooling, the expansion, the char formation, they're framed as being more like smart materials that react to the threat, forming an oxygen shield, rather than just being an inert barrier, a different, potentially higher level of protection for complex situations.
Got it. Now, for the engineers and product managers listening, meeting safety standards is obviously non-negotiable. What do the sources say about compliance and testing?
Yeah, that's critical. The material emphasizes meeting really stringent codes. They list examples like UL263, ASTM E814, ASTM E119. Those often relate to building construction fire resistance.
Right, like fire ratings for walls and floors.
Exactly. Then UL10C for fire doors, UL94 for plastic flammability, UL1973, which is specifically for battery energy storage systems, plus various automotive standards. It's a complex landscape.
And do these intumescent products measure up?
The sources claim that specific products are developed and tested precisely to meet these standards. They give examples like certain materials achieving that 40x expansion needed for some fire stop applications under UL263 or ASTM E814, or others being tested against the relevant parts of UL1973 for use in battery systems.
So the claim is they're not just theoretical, they're being validated.
Yes, and it's mentioned that this involves ongoing R&D, lots of real-world scenario testing, and working closely with certification labs like UL to really validate the performance under the extreme conditions they might face.
Okay, last big point from the material, cost effectiveness, the ROI. How do these potentially more advanced materials actually pay off? Is it just about the upfront cost?
Not usually, no. The perspective in the sources is much more about life cycle savings, the total cost of ownership, or TCO. That's often the key metric for adoption, especially at scale.
So where do the savings come from, according to the sources?
Several areas. One is potentially fewer components. If one molded intumescent part can do the job of a structural piece plus separate insulation layers.
Simpler assembly, fewer things to buy.
Right. Then reduced weight, especially compared to metal or multi-layer solutions. That means lower shipping costs, easier handling, and in EVs, better efficiency and range.
Right.
Quick installation is another. Pre-molded parts often mean less fiddly on-site labor compared to cutting and fitting blankets or sheets.
Less time on the assembly line or construction site.
Exactly. Lower maintenance is also suggested, as these solid parts are less prone to wear, tear, or delamination than some complex layered systems might be over time. And maybe the biggest factor, risk mitigation.
Avoiding the disaster scenario.
Precisely. Preventing a major thermal runaway event avoids potentially enormous costs. Property damage, product recalls, liability, brand damage, and most importantly, protecting lives. That value is hard to overstate.
So the argument is look beyond the price per kilo of the raw material.
That seems to be the strong suggestion. When you factor everything in assembly, weight, maintenance, and especially risk reduction, the sources argue that Intumescent solutions often come out ahead on total cost of ownership compared to older approaches, particularly for high-volume manufacturing or large, critical projects.
Makes sense. And looking ahead briefly.
The material just touches on future innovations, really suggesting this field is still evolving. They see, more synergy between the material science itself and clever industrial design pushing the boundaries of what these materials can do.
Okay, let's try and wrap this up. What's the core message we're getting from these sources?
I think the main takeaway is that intumescent thermoplastics are presented as a really significant development, a potential paradigm shift in how we protect critical systems, buildings, ESS, EVs from serious fire threats like thermal runaway and arcing. The key claim is they offer a higher level of active containment and fire retardants than traditional passive insulators like Mica or Aerogel, mainly because of that dynamic expansion and char formation.
And they're easier to integrate, potentially better TCO.
Right. Easier to use in complex designs via molding, potentially more cost-effective over the product life cycle, and engineered specifically to meet those tough modern safety standards. The sources also cite specific companies, like Pyrophobic Systems Ltd., as examples of players who've invested decades in developing these engineered solutions to solve real headaches for engineers and project managers.
So what does this all mean for you, our listeners?
Well, the sources definitely paint a picture of intumescent thermoplastics as a powerful, maybe even essential tool emerging in the engineering world, especially for tackling these really critical fire safety challenges that come with packing more power into smaller spaces.
Yeah, the challenges aren't going away.
Definitely not. And it leaves us with maybe a provocative thought to chew on based on all this. As our technology keeps getting smaller, denser, more powerful, how much more will we need to rely on materials that don't just passively resist danger, but actively react to it? And beyond just safety, what other kinds of new design possibilities might that unlock down the road? Something to think